and 6.3. So let's start with our first example. And today we're going to do what we didn't do last time, is do a rotation about a non-axis line. So that's what we're going to do today. So let's start with, say I want to find the volume of the solid obtained by rotating the region bounded by y equals x minus x squared and y equals 0 about the line x equals 2. Okay. So I need to picture this region. Right? First step, always picture your region. You need to see what we're doing. So I look at my problem. I see two curves that bound my region. What am I going to do with those two equations? Set them equal to each other because we want to find the intersection points, right? The way we find intersection points in this case, I'm going to set these two equations equal. All right, so let's do that. 0 equals x minus x squared. Now what? Factor? What can I factor? An x out. And I get two solutions. I get x equals 0 and x equals 1. Now these two values correspond to points. You take these x values, plug them into either function to get your points. The easier function is y equals 0. So your 2 points, intersection points, they're going to be 0, 0 and 1, 0. Great, we have our intersection points. I'm going to start by plotting those on my graph. Maybe I'll go a little bit lower. Oop, why don't you do that? Nope. Okay. All right. So I said 0, 0 and 1, 0. Y equals 0, that's just our horizontal line. It's just the x-axis. And now I need to plot the graph of the other equation, x minus x squared. That's a parabola. It's going to point downwards. I need one more point for a parabola. So, I don't know, plug in a number between 0 and 1 into your function to get another point. So I'm looking at the equation y equals x minus x squared. Let's plug in 1/2 into this. And you'll get 1/2 minus 1/4, or just 1/4. So at 1/2, it's 1/4. So it's not very tall. Let me make this a little bit larger. Okay. So it looks like that. So the region I'm interested in, it's this little mound, this little hill right here. Okay. What am I rotating about? X equals 2. So let's draw our rotation line now. 2. That's a vertical line. And I want to rotate about that. So when we're doing cylindrical shells, remember our strips now are parallel to our rotation line. So which way do my strips go? Do they go horizontal or vertical? Vertical. Okay, so when I draw my little strips in here, I want to draw them up and down, vertical. So let's say like this. Okay. Now when you're using the method of cylindrical shells, I need two things. I need my radius, r, and my height, h. But before I do that, maybe we should mention what variable are we going to integrate with respect to. My strips, they're vertical, right? There's a top and a bottom. When I have a top bottom, that means we're going to integrate with respect to x. Yes. Okay. So our integral should be in terms of x. All right. So now we're ready. Let's find r and let's find h. The height of my, let's do h first because it's a little bit easier. The height of my strips, it comes from this parabola function, right? It comes from how tall the function is, which is y. So the height is just going to be my function x minus x squared. This part is just like if you rotated about the y-axis, x minus x squared. The part that's different is our radius. So our r, how are we going to find that? Let's look back at our picture up here. And I want the radius. Remember, that's the distance from my strip to my rotation line. So that would be this value right here. That's our r. I can't find that directly. I got to view it in kind of like pieces. So what I could do is I could measure this whole distance here. What's that whole distance there? 2? Stays the same, right? But now I've counted too much distance, right? Too much. Because my blue line is shorter than this red line. So I need to subtract this extra distance right here. The 2, that's the distance between here and here. It's 2. I know I covered up the 2 there, sorry. There. That helps. All right. So I need to know what is that distance of that short little red line here. That's a horizontal distance, and so that's just x. And I'm integrating with respect to x, so I'm good with that variable. Okay. So this distance right here, this is x. So to get r, it's going to be the difference of the 2. It's going to be 2 minus x. So it looks like I figured out now R and H, and I'm good to go. Yep.
The X, the strip, or that little area between the strip and the T?
So the X is that red distance. Let me go back up to the picture. It's the distance from here to here up till you start your strip, essentially. Because remember, this strip is really thin. I draw it a little thick, but it's really a thin kind of thing. So this distance out here, it's from the y-axis over to my strip, which is just defined to be x. Okay. Are we all okay with how we get r? It's the difference because I had to subtract. All right. Let me scroll up. Once you know R and H, you just got to plug it into your formula. So when we were doing cylindrical shells, our volume, it's 2 pi, the integral of R, which is 2 minus x, times H, remember, think circumference, 2 pi r, and then h is the height, and the dx represents my thickness. And now I need to know what bounds go here. So what are my bounds on this integral going to be?
Would be 0 and a quarter.
So hold on. Let's look back at our region. Which variable do I have in my integral, x or y?
Oh, X.
X. So let's look back here. X. What does x go between? 0 and 1 for my region. My region starts at x equals 0 and it goes to x equals 1. But yes, if we were doing y, it would be 0 and a quarter. I think that's the whole time. Okay, so 0 to 1. So then you just FOIL all this stuff out in the middle. You'll get 2x minus 2x squared plus x squared. Nope, minus x squared minus x squared plus x cubed. And again, if it was me, I would combine your like terms because then that means you have less to plug in numbers into. So I would combine this, this minus 2x squared and this minus x squared. Combine it into a minus 3x squared plus x cubed. Okay, and then you integrate. 2 pi x squared minus x cubed plus x to the 4th over 4. And plug in your numbers from 0 to 1. Looks like pi over 2. Okay. So I'm hoping that you see the pattern in how we do all these problems. We find intersection points if you need to, draw the picture of our region. And if you're doing cylindrical shells, you should, well, I always start by asking myself, what variable am I going to integrate? What variable is going to appear in my integral? And then find R and H, plug it into the formula, and integrate. Okay? Okay. So,
Why we put the R and H, like how we use the formula.
yeah. So what we're doing is we're getting, when I rotate this strip around here, I'm getting this thin cylinder. And so the way we calculate the volume of that cylinder is it's the circumference. So we had this formula last time. Let me put it here. To get volume, it was circumference times height times thickness. Well, when I rotate that around, I'm getting a circle. So the circumference is 2 pi r. The height is h. And my thickness is dx. Because I'm taking a very thin strip when I rotate that